Good evening everyone. My name is Renu Raman Sahu and today we will be discussing about the fourth week of Physics of Materials course, and we'll be discussing some of the previous year assignments so that you can learn how to solve the questions of this year. So in this week what we discussed was about large systems and the statistical mechanics, how statistical mechanics come into play. But at the hindsight what we need is that what we are dealing with in different subjects. For example, in chemistry and metallurgy, uh, most of the systems we deal with are at constant temperature or constant pressure. This is because it is easy to impose the experimental conditions of constant temperature and pressure. In particular, in the field of metallurgy, the pressure is taken as 1 atmosphere because most of the mines or minerals that you deal with, those are mostly available in the earth's surface, which at which the pressure is 1 atmospheric pressure. But in physics what we deal with is with systems, and those systems uh, with constant volume. So this is because mostly we try to keep the volume constant because at constant volume the energy levels of the system would be fixed. So that is why, since the energy levels are identifiable at constant volume, we try to keep the v constant. So with this in hindsight, we'll go ahead. So what do we mean by large systems? A large system, for example, let us take a 1 meter cube of a particular metal, for example copper or silver. So in 1 meter cube, if we calculate using the mole concept, then what you get is around 10 to the power 28 atoms, or if it is univalent, of this order of free electrons. And second thing that we want to be considerate about is the energy associated with the system. At a constant temperature, there is an average energy that is associated with the system, and in a large system we don't want to, like, this is 10 to the power 28 atoms, and we are not interested, neither it is useful for us to know what is the energy of each and every of this atom. Rather what we need is an approach that will enable us to make statements about the system as a whole, like what is the average energy of the entire system. Not We don't want to know what is the energy of each and every a single atom or molecule. So this approach is called statistical mechanics, in which we have the knowledge of the individual uh, particles, the energy levels of the uh, individual atoms or molecules, and from that we want to predict what would be the behavior of of a system which consists of large number of those individual molecules or atoms. So this is the approach of statistical mechanics. Why this is important? It is because, like, recently we studied the Drude-Lorentz model, in which uh, the object of study was the free electrons, how a large collection of electrons behave to get the conductivity, the thermal conductivity, electrical conductivity, and so on. So there is a concept called macrostate. Macrostate is something which can be specified by experimental conditions. For example, in experiment we can fix what is the temperature, we can fix what is the volume, and we can fix the energy of the system. Okay, or energy with respect to a particular reference, we can fix that. Or we have a technique to measure these things experimentally. So this is a given a particular macro state, but that particular macro state can be attained by different configurations of atoms and molecules, and each of those configurations of atoms and of its constituents of, let's say, atoms, is called a microstate. So for example, let us consider at a constant temperature and constant volume. Why constant volume? Again, because if we fix the volume, then the energy levels would be fixed. And let's say, let us look at an example at constant temperature, constant volume, and constant energy. And each of these atoms will have, let's say they have this four energy levels: 0, 1, 1e, 2e and 3e. These are the four energy levels, and we'll look at systems with 2 particles, 3 particles and 4 particles. So what is a macro state? A macro state is something which is labeled by the temperature, the volume and the total energy E, and corresponding to that we can have multiple micro states. So let us look at the 2 particle case. In 2 particle case we want to have energy of 3e. How can we get 3e? We can get 3e by two methods. One is 2e is 2e plus, so we have 2 particles, right? One particle in 2e energy level and another particle in 0 energy level, or one particle in so we want 3e. So this is one of the configuration, or what are, we have 3e energy level as well. So these are the two different ways in which we can have the energy 3e. So this corresponds to 3e, this particular microstate corresponds to 3e plus 0e, and this corresponds to 2e plus 1e. Now this is a microstate with corresponding to the macro state labeled by these 3 levels, T, V and E. So, and what is the number of ways to obtain this microstate? So here one thing we have to keep in mind, that the particles that we are considering are identical but they are distinguishable. So we can say that okay, this we can actually put a label that okay, this is particle 1, particle 2, even if although attributes of those particles, for example the mass, charge, whatever the properties they have, they might be same, but an important factor here is to note that they can be distinguished. That means we can put a label on them and say that okay, this particle can be treated as a different particle from the another particle. So if we look into that way, then we can have two states, because like in one, let's say this is particle 1 and particle 2. So particle 1 2, this is one configuration, particle 2 1, this is another configuration. So there are two ways in which this microstate can be obtained. So microstate 1 can be obtained in two ways, similarly microstate 2 can be obtained in two ways, and these two microstates correspond to the macrostate T, V and energy is equal to 3e, and this is also fixed and temperature is also fixed. This 3 they label a microstate. Okay, now if we, what happens if we increase the number of particles, let's say to 3e. So we have 3e, now we have, let's say 3 particles now. So when we have 3 particles, so the number of ways in which the energy 3e can be obtained also increases. How? Because now since we have 3 particles, so this is one configuration where one particle is in 3e and the other are in 0 energy level. So one particle in 2e, one other particle is in 1e and the other particle is in 0e, or the 3 particles can be in 1e, 1e, 1e. These are the 3 ways in which we can have the 3 ways in which we can obtain the energy 3e. Now how do we let us calculate how many ways this microstate can be obtained. So this microstate can be obtained in 3 factorial by 2 factorial into 1 factorial. So what you have to do, the total number of particles divided by the number of particle in one box. So you can think of this as different boxes. Okay, and the problem is similar to dividing 3 particles into 2 boxes here in this case. Here it is dividing 3 particles into one box, into 3 boxes, and in how many ways you can do that. And this is putting three particles in one box. In how many ways you can do that? So it is just given by 3 factorial by 2 factorial into 1 factorial. So here the number of particles in each box that will go into this denominator. So if you calculate that, so in the first case we get 3 ways, the second case we got 6 ways, and here we got 1. And if we look into the ratio of probabilities, then it is 30% is to 60% is to 10%. Whereas uh, when it was in a two particle system, in two particle system it was 50%, there was a 50-50 probability of both the microstate. So what we see here, as we moved from two particle to three particle, then the probability of microstates start to differ. So here the microstates, both microstate and microstate 1 and 2, they both were in same probability. Now you see that there is a difference that is coming up, and one of the microstate is becoming distinctly more probable. So here you can see that it is 60% probable, the next one is the 30% probable. So this is twice as probable as the next most probable microstate. Now let us see what will happen. So and remember, we are doing all this for identical and distinguishable particles. Now what will happen if we increase the number of particles to 4 particles? So in 4 particle case, so again what we want is a total energy of 3e, and this can be obtained in many ways now, in this following 3 ways. So in one way it is one particle is in 3e and other in 0e, one in 2e, one in 1e, and the two others are in 0e. And this is another case where these three particles are in the these three particles are in 1e and one particle is in 0e. Now similar maths will apply for what is the number of particles correspond number of ways in which this microstate can be obtained. It is 4 factorial by 1 factorial into 3 factorial, which is 4. If you calculate for this, it will become 4 factorial by 1 factorial, 1 factorial, 2 factorial, which is 12. And if you calculate for this, it comes out to be 4. Now you see, and if you look at the ratios, it will come out to be 20%, 60%, and 20%. So one, this is the most probable microstate, and this most probable microstate is, now you see, it is thrice as probable as the next probable microstate. So in two particle case all were equiprobable. In 3 particle case one was twice as probable. Now it is thrice as probable. Now if you do that for higher, like let's say 5 particle system in which you want to obtain 3e energy, then you will have one state which will be more probable than all others. Now you see here, so if you take the sum of this probability and this probability, which is 40%, whereas this single state is 60% probable. So the probability of the system to be in this state is more likely than all other states combined. So what we conclude from here? We conclude that as the number of particles, as the number of particles will increase, so this we considered up to 4 particles. Now imagine if we have 10 to the power 28 particles. So it is really huge number. And for this, so what is the trend we observed? As the number of particles will increase, the most probable microstate of the system becomes more probable than all of the other microstates combined. Okay, just like here we saw that this is a microstate, this is another microstate, and if you just add the probabilities of both of this, then the probability of these two microstates, yeah, so hello,
Sir, good evening. Sorry, I got late in the call.
yeah, no problem. So I was just uh, I was just discussing about this probabilities. Did you go through the lectures of the previous class or what?
Previous class, yes, I did. This week I have not started, but last week, yes.
Okay, okay, okay. So, like what?
The derivation for um, the equation that we spoke about, and Boltzmann constant, and relation between the theory of what is that? The, um, what is, I forgot the name, but yeah, I did go through that
Okay,
completely.
okay, fine. So, like this week, okay, this week, what was the this that we are trying to understand the thermodynamics of the system, okay, from a microscopic point of view, and then we want to just see how. So okay, the big picture is that the big picture is that we saw Drude Lorentz model, right? It had certain shortcomings, some things it couldn't explain,
Yes, yes,
and why it couldn't explain. We want to get into the root of that, and we had discussed about something called Maxwell-Boltzmann distribution that the ideal gas will follow. So we want to understand where in the so what is the difference between the particles which constitute the ideal gas and the free electron gas, like what is the difference between uh, a classical particle and the electrons, so why they are differing. So here we just started discussing about the approach called statistical mechanics. So what we are trying to do here is we are looking at a very large system of the order of.
so it's a Maxwell Boltzmann versus Ruth Boltzmann, Ruth Lawrence that we discussed last week. Is that
Root.
right? Usually the Maxwell Boltzmann is for ideal gas.
Yeah, yeah. We here uh, here what we are trying to do. We want to see what is the Maxwell-Boltzmann distribution.
Yeah,
Okay. So and we want to do it from a statistical mechanics point of view.
sure.
Okay. Like I don't know what is your background. Your like have you taken any physics course, statistical mechanics before?
Yes, but it's been a long back because I passed my masters in 2006.
Oh, okay, okay, okay. Maybe
It's
I will
already
just quickly go
yeah.
through
Please
this.
brush up me. Yeah, that will be better. Yeah,
Yeah.
thanks.
So what we do in statistical mechanics is we want to look at what is so we want to understand the thermodynamics of the system from the microscopic point of view. Okay, so we call something a macro state which can be labeled by these parameters, like a particular macro state at constant temperature, volume, and a particular energy E. Why? Because this can be experimentally fixed. Okay, so that is why we fix these three parameters, and corresponding to that there can be many different configurations of the atoms and molecules which can give this same value. Those are called the microstates. Okay, so as an example, we and why we want to fix the volume here is because from a physics point of view, if we fix the volume, then the number of energy levels or the energy levels are clearly defined. Like if you have done like a particle in a box problem, then if you fix the length of the well, then the energy levels get fixed. So that's the thing. That is why we want to, and we want to understand the microscopic interactions, what is going on. So that is why we want to fix the V. So here we are trying to say that each of the atoms of the, like we are taking a system in which each atom is has this four energy levels: 0, 1e, 2e, and 3e. And we want to understand how we can get the total energy 3e at constant temperature and volume. Since volume is constant, these energy levels won't change. Okay, and when we look at a two particle case, let us say that system has two particles and two of the particles have these energy levels. So in how many ways we can get 3e? So in one case, if one particle is in 3e and other particle is in 0e, then we can get uh, this particular microstate, and another microstate is when one is in 2e and other is in e. Okay, so now what these two particles, what we are considering, these particles are identical and distinct, but they are distinguishable. Identical means the properties of both the particles are same, but we know that, so we can identify that okay, this is particle 1 and this is particle 2, even if their position interchanges or uh, like interchanges or something will happen, we know that okay, this is this particle and this is the other particle. We have a way to distinguish them, and classical particles are always this distinguishable. So how many ways these two particles can fill these two energy levels? So it is like putting two balls in two different boxes, and each of these boxes one particle. So it is this 2 factorial by 1 factorial 1 factorial. So this microstate can be attained in two ways, and the other microstate similarly in two ways. Now we have the same problem, but we'll increase the number of particles. Let's say what will happen in case of 3 particles. So for 3 particles, we want to find how we can attain the total energy 3. So this was the case of 2 particle. In the 3 particle case, what we can have is, so these are the 3 particles. So one particle is in 0e, other particle is in 0e, and the third particle is in 3e. This is one way. And the number of way this can be attained is 3 factorial by 2 factorial. So 2 factorial corresponds to 2 particle in the 0e energy level, and 1 factorial, this corresponds to 1 particle in the 3e energy level. Now for another microstate can be this, where one particle is in 2e and the other particle is in 1e and the third particle is in 0e. And number of ways this microstate can be attained is 3 factorial by 1 factorial 1 factorial 1 factorial, where each of this 1 factorial correspond to number of ways this one particle can be put in this one energy level. Okay, and the third way is 3 particle, number of ways the 3 particle can be put in
So
this
when we
one
say
energy
this
level.
3 factorial divided by 2 factorial, 1 factorial,
Yeah,
or 3 factorial divided by 1 factorial, 1 factorial, 1 factorial, so we mean that the energy state, for example, 3 factorial is the total number of energy states,
total
and in the
number of
bottom,
particles.
particles. Okay, so the bottom is the energy states at energy level 2 versus energy level 1, and the other one is energy level 1, 2, 3. The last one is all in the same energy level. Is that right? Or
Yeah, yeah. What this means is particle 1, this particle, this particle, this particle, these 3 particles are in one energy level. So if you add the total energy 1e, 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 it becomes 3e.
yeah.
So this is a microstate corresponding to the macrostate, the temperature, volume, and this energy. Okay, we're fixing the energy. So this is the energy of the system, and we want to count how many ways this uh, macrostate can be obtained. You got the point, right?
Yes. Yeah.
Yeah. So these are the 3 microstates in which that can happen, and each of these microstate can happen in these many ways. So for example here, so you imagine 3 particles, and you can think of it as 3 box, and you can think of 1 2 3. So so how it can be 6 ways is because uh, let me just, so one way can be you put particle 1 here, particle 2 here, particle 3 here, then particle 1 here, particle 3 here, particle 2 here, then particle 2 here, 1 here, 3 here, 2 here, 3 here, 1 here, yeah, 3 2 1 3 1 2. So these are 6 ways in which this configuration can be attained. And the fact that I can label these particles 1 2 and 3, that says that these particles are distinguishable particles, so we can distinguish between each particles. Like, you got the point, right? What it is being done.
Yeah. So total 6 ways. Yeah. 6
You
ways
see,
is
this is one way,
1 factorial, 1 factorial, 1 factorial. 3 ways
this is
is
one way, two way, three
1
way,
way.
four way, five way, six way.
How this 3 ways comes, sir? How do
Three,
you arrive at it? 3 into 2 into 1 divided by 2 into 1. Okay, 3 into 1. Okay, got it. Got it. Yes.
yeah. And like, you can actually count how this thing, so this is just some simple combinatorics, so that so it is just dividing three distinguishable balls in two boxes. And how you can do that? Two boxes that you can think of it as 3e energy level and 0e energy level. You got it right? So that's how it is.
Yes, sir. Yeah.
Yeah.
3
And
is to 6 is to 1. Okay.
yeah, so the point to note here is that as we moved from so
Most likely state is like, how did you come to this is the most likely state is like
yeah,
two energy
yeah,
levels.
I'm just going to tell you. So you see,
Maybe I just need some one more time, sir.
yeah, see. So why it is so you got these numbers right? How you can get this three-way, six-way, and one-way? Is this part clear? Three particle system. Uh, what is the doubt? See, what we are trying to do here is, suppose we have a particular macro state, okay, where we are fixing temperature, volume, and energy. Then we are
Yeah.
asking ourselves the question: if I have n number of particles, in how many ways I can attain this configuration? Okay, and it turns
Which
out,
configuration, sir? What like is there a criteria for the configuration that we are looking at?
yeah, the criteria is that the temperature, volume, and energy has to be fixed, and the constant. Currently, what we are looking at, how we can get the energy 3e. You got it right here. So here, this is our criteria for now as an example.
Energy level 3B, huh? Okay.
Not the energy level 3e. The total energy of the system has to be 3e. Okay, and
Okay, yeah.
what does the system consists of? The system consists of the atoms. So this is atom 1. Let's say this is atom 1, atom 2, atom 3, atom 4. So, and these atom will have certain energy levels. It has energy levels 3e, 2e, 1e, 0e. So this is the energy level corresponding to this atom. This will also have its own energy level: 3e, 2e, 1e, and 0e. It is the energy level of this. It will have its own energy level. It will carry its own energy level. So there are different. So this is particle 1. Let's say particle 2, particle 3, particle 4. Now here is the system that you have to build. And if I give you only two particles, particle 1 and 2, okay, then in how many ways you can build this macro state? Is the problem clear? What you are trying to do?
Yes, sir. Yeah, it's clear now.
Yeah. So, like if I give you two particles, then in how many ways you can create 3e energy level? So what we are saying here by this notation is that one particle is in 0e energy level and the another particle is in 3e energy level. This is one way in which you can create the uh, the macro state that is given to you. Okay, so one particle is here, second particle is here. Another way is one particle here, second particle is here. Okay, so there are two ways in which we can make this microstate, and this microstate corresponds to a macrostate which has energy 3e. That part clear?
Yes, got it.
Okay, now in the right column, what we are doing, in the right hand column, what we are looking at is, if I give you one more particle, so we have the system is fixed, the temperature, volume, and energy is fixed, and you have to build that system out of now three particles. So when you have three particles, in how many ways you can create that macro state? It turns out that you can create that using these three microstates. The one which is shown in green, the one which is shown in this maroon and in violet. Okay, so what this green state, the green microstate, what it means is that one particle is in 3e and the other two particles are in 0e and 0e energy level. Okay, and the number of ways in which that can be done is 3 ways. Is that clear?
Yes, sir. Yeah.
Yeah. Similarly, like you have to like you just maybe need to think a bit. So it is just similarly like distributing balls in a box. Okay, so what it turns out is that we have now certain microstates. Okay, and each of these microstates will have certain number of ways in which that can be attained, and each of the way corresponds to the configuration of individual atomic uh, the individual atomic energy configurations. Okay, so what it turned out, it had, when we have three particles, we have energy, we have the probability 30% of being in micro, let's say this is microstate 1, microstate 1, 2 and 3. So in microstate 2, it can be attained in 6 ways, whereas microstate 1 and 3 can be attained in 3 ways and 1 way. So now what is the assumption of the statistical mechanics is that all of these ways are equiprobable. Okay, so so when you take a random snapshot, so there is 60% probability. So how we get so if you take all this sum of all this probability as 1. Okay, so 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 what is the total number of ways in which the microstate can be obtained is 3 plus 6 plus 1, which is 10. So out of 10 ways, so the total number of ways is 3 plus 6 plus 1 is 10. So out of 10 ways, in 6 ways the particle can be in configuration 2, in this configuration. So this is the most probable microstate. Okay, you got it right? Why this is the most probable microstate? I hope that is clear.
So total 10 possibilities.
So out of 10 possibilities, because 3 ways in 3 ways uh, this microstate can be obtained, 6 ways
Yes.
this microstate can be obtained, and 1 way this microstate can be obtained. So there are total 10 ways in which the 10 microstates in which this macrostate can be obtained. Okay, and 6 of those correspond to microstate 3, microstate 2. Okay, so when you look at the system randomly, then you are most likely to find this configuration in which one particle is in 2e, other particle is in 1e, and the third particle is in 0e. Okay, so it will be more clear if you look at the four particle system. So now if I have 4 particles and I want to achieve the same energy level 3e, okay, then that can be done in this many ways. Let's say this is one way in which it can be done: 3e, 0e, 0e, 0e. These are 4 particles, and the number of ways in which this microstate can be accomplished is 4 factorial by 1 factorial 3 factorial. Like if you are not able to like visualize right now, you can just learn this as a trick, that the numerator will have the total number of particles and its factorial, and the denominator will have so the number of particles in each of this energy level. Okay, at least this will help you to solve the problems. Okay, there is one problem we are going to discuss today based on this concept. So the another way in which you can get a microstate is 2e, 1e, and other 2 particles are in 0e. And the number of ways in which this microstate can be obtained is 4 factorial, 1 factorial, 1 factorial, 2 factorial, and if you calculate that, it will turn out to be 12. And the third one is this microstate, which can be attained in 4 ways. So the total number of ways in which the macro state 3e can be obtained is 4 plus 12 plus 4, total 20 ways. Out of the 20 ways, 12 ways corresponds to this micro state, and if you look in terms of percentage, it is 60%. So if you take a random snapshot, then it is most likely that the system will be in the configuration, in this configuration, in this green color configuration. So what we observe here is that as we increase, as we move from 2 particle to 3 particle, then the first thing that we observed is that probabilities of the microstates start differing. So here we had 2 microstates and the probability was same, 50%, 50%. And when we increase the number of particles, so it is the probability now differed, 30%, 60%, 10%. And another observation is that one of the microstate is becoming distinctly more probable. So here you see the 60% is twice as probable as the 30% microstate. But here the most probable one is 60%, it is thrice as probable as the next best, next most probable microstate. Okay, so the conclusion is that as you increase the number of particles, so we saw with 4 particles, then we can ask with 5 particle system how in how many ways we can arrive at this 3e microstate. If you do that, then we can look into 10 particles, 15 particles, but in reality we'll have 10 to the power 28 particles per unit volume. Okay. So what will happen is the number of particles will increase and the most probable microstate of the system will become more and more probable than all other microstates combined. So here you see, this is the most probable microstate, it has 60% of probability, and if you combine the other two, this 20% and 20%, which if you sum them, it is like 40% more probable, but the most probable microstate is 60%, which is more probable than the other two probabilities combined. So this is what is happening, this is the trend that we have to observe. Okay, so in statistical mechanics, the gist of statistical mechanics is that the equilibrium state is the one in which the equilibrium state is the most probable state. So for example, here it is 60%. So when you go to 10 to the power 28, this will become 99.99 and all other will sum up to less than 1%. Okay, so the most probable state is the equilibrium state. That is the statement coming from the statistical mechanics. So what we are going to do now is to use this concept, that will look at the most probable state, and we want to understand, we want to get into what is the Maxwell-Boltzmann statistics. So let us fix that we have the total n number of particles in our system, and the volume is fixed. Since the volume is fixed, the energy levels of the atoms in that volume are fixed. And one thing we have to keep in mind, that in Maxwell-Boltzmann statistics we are looking into identical particles, but they are distinguishable, just like we saw in previous example. So in Maxwell-Boltzmann statistics, now the question that we want to answer is, what fraction of particles, let's say we have total n number of particles, okay, so but not all these n number of particles are in certain energy E. So we want to find what is the fraction of particles and at what energy they are in. Okay, now let us look at one individual atom. One individual atom can have certain energy levels. Okay, let us name that energy levels E1, E2, E3, E4, ER. Up to they have ER energy levels. Now if you look at the atoms in the system, then the atoms can either be so if you look at a particular atom, it can be either in one of these energy level. Okay, let's say out of those n naught are in energy E naught. N1 particles are in energy E1, N2 particles are in energy E2, N3 particles are in energy E3, and so on, and Nr particles are in energy Er. Okay, so basically what I am saying is Ni particles are in energy Ei. Okay, and the number of ways of attaining a given microstate, how we can obtain this microstate? So it is, so this formula is just similar to the one which we saw in the example. Okay, so it is n factorial divided by n naught factorial, n1 factorial, n2 factorial, so on n r factorial. Like you got this point, right? Why this happens? It is
Yeah,
just,
somewhat, sir.
yeah, it is
Somewhat.
similar
Yeah.
to this. Okay,
Yeah.
I hope you know the fact that 0 factorial is 1. 0 factorial is equal to 1. This you know, right? If not, then it is the fact. You take it as a fact. Okay. So what is happening is, for in this case, n is 4. Okay, and n and we have n naught is n naught equal to 1, n naught equal n1 equal to here 3, and 2 is equal to 0, and 3 equal to uh, and 3 equal to how much? It is 0, because there are no particles here. You got it right from this example?
Yes, sir. Yeah. Yeah.
Okay, cool. Yeah, so similar to that, so the number of ways in which a given microstate can be obtained is, if you look at this example, sorry, if you look at this example, so it is 4 factorial divided by 3 factorial. This is n naught, uh, n naught factorial, n1 factorial, then again, okay, sorry, so here it is 0 factorial, 0 factorial. So these are the ways in which we are filling this energy level. You got it right? This is, so it is similar to that. Here omega is equal to, this is another omega, this is another omega. Okay, and our problem now here is to find the maximum omega. The maximum omega in this case is this one, the 60% one. So what we are trying to do here is, we are looking at this energy state. We are given a microstate. We are given this microstate. We are looking at the number of ways in which that can be obtained. Okay, and what is now the question is, what is the statement of classical the statistical mechanics? It says that the equilibrium state is the one for which this is maximum. So this will be maximum if we can find that set of n0, n1, n2, and r which will maximize the omega. So now the task is to find what is the maximum of this omega. So let us do that. so we have this, expression. This is the number of ways in which a particular microstate can be obtained. What we are going to do now is, so this is just another way of writing it. The product of this ni factorial can be just written as like this. Okay, now if, so basically logarithm is a increasing function. Okay, so if we maximize omega, the point at which omega will be maximized is the point at which log of omega will be maximized. And the advantage of taking log is that we can convert this multiplication and division into the into sum and differences. So it is just so I hope this step is clear. Then what we are going to do, we are going to use something called Stirling approximation, which is really valid for large x or large value of numbers. So which says that the logarithm of a factorial, let's say x factorial, is x ln x minus x. We are just going to use that for this equation. So ln omega is so log of n factorial is n ln n minus n using the Stirling approximation. And similarly here uh, we get ni ln ni minus ni. So ni, since it would usually n are the large value, so out of 10 to the power 28, so these are very really large numbers, and for that Stirling approximation really holds good. Okay, now what we want to do, we want to maximize ln omega, so that what if we take a derivative of that, this delta ln omega, it should be 0, it should be 0 at maximum omega. Okay, so if you calculate that, so n is a constant, and we are fixing the total number of particles. Since we are fixed that, so delta of this will be 0. So by delta I just mean the derivative. Okay, and here delta of this function we have to take. When we take the del of that function, it is del ni. We have just applied the chain rule, and applying the chain rule we just get this expression, and here this will cancel with this, and what we obtain finally is this delta ni into ln ni. Okay, and we want to so that will be equal to 0 at maximum of at max omega, and max value of omega is the equilibrium. Okay, so this condition is the condition for the equilibrium state. Now we have three we got the equilibrium state. The equation 1 is the condition for the equilibrium state. Now since the total number of particles is constant, so sum over ni will be constant, and if you take the derivative of that, so sum over delta ni will be constant. Okay, and the another thing we want to impose is that the total energy has to be constant. The total energy, what is the total energy? We are saying that n0 particles are in energy E0, n1 particle are in energy E1, n2 particle are in energy E2. So if you sum all the energies of all the particles, sum the energy of all the particles, then you get this expression. And this EI are constants because the volume is constant. Since B constant implies EI constant. So this delta ni, so if you take the derivative of that, it is just EI delta ni. So these are your two constraints. So constraint number 1, constraint 1, and constraint 2. Okay, so we want to maximize this function subject to constraint 1 and constraint 2. These type of maximization problems are usually dealt by something called Lagrange's method of undetermined multipliers. So what we do is we multiply each of these constraints with certain so this is constant, right? So if you look at the right side panel, so this is a constraint, this is one constraint which fixes the number of particles, and this is another constraint which fixes the total energy. So we are multiplying these constraints with an unknown or undetermined multiplier. These are unknown yet, alpha and beta. These are some constant which we are just multiplying, and this is the function that we want to maximize. So what we are trying to do, so we just sum all of this. So this equation plus alpha times this equation plus beta times this equation, that has to be equal to 0. So when we just put that, so it is delta, and we take the delta ni common. So on adding all these three equations, equation 1, 2, 3, along with Lagrange undetermined multipliers, we get an expression something like this. Now this at maximum omega, at max omega, irrespective of what delta ni is, this equation has to be 0. The sum of this has to be 0. This entire thing has to be 0 irrespective of what delta ni is, and that is possible if each of these individual term is 0. Okay, I hope this argument is clear. uh, like this is an argument from linear algebra. If not, then maybe you can go through this basic arguments, that will be helpful. So the argument is that at maximum omega we want this entire expression to be 0 starting from here. This has to be 0.
Not constant is basically based on two constants, right? Two constant values. Based on that, we are getting the Lagrange equation.
What? Can you please repeat?
Yeah, the Lagrange like equation is coming from the two constants, or two standard constants. Based on that,
Two constants. Yeah, there are two constants. Corresponding to that, there are two Lagrange multiplier.
okay. So what are the Lagrange here?
Huh? What?
What are the Lagrange here? The undimensional multipliers.
Sorry, you're not that audible. Can you please?
Lagrange values, the multipliers that we're using here, is the delta ni and
No,
no,
no.
it is all
Lagrange multipliers are alpha and beta.
alpha theta. Okay, got it. Okay, yeah.
Yeah. So what we are trying to do is we want to equate this to 0, and this can be 0. This has to be 0 irrespective of what the value of delta ni is. Okay, irrespective of what delta ni is. So this can be 0 only if this expression is 0, the one in this box. So that, so regardless of delta ni, the above expression has to vanish always. So we got this expression. Now what we're trying to do a sort of rearrangement. So ln ni is equal to, we're taking this to the right hand side, and since this is logarithm, we are putting all in the exponent. So ni turns out to be e to the power minus alpha e to the power minus beta epsilon I. So we have now a relation between ni and ei, that something tells you ni number of particles are in ei energy level. Okay, and but now we still have to determine what is e to the power minus alpha and what is this beta, the two Lagrange multiplier. So we obtained that this is the distribution. Okay, this distribution, so the nature of this distribution is called Maxwell-Boltzmann distribution. Now we just want to find what are these undetermined multipliers. So we have this constant, the constant number 1, that sum of all the individual energy states should be n. So I equal to 1 to r e to the power minus, so I am just putting the expression that we got above, and it, since alpha is a constant, e to the power minus alpha can come out, and the value of e to the power minus alpha turns out to be, so we are taking this to the denominator, and what we got is e to the power minus alpha is n over sum over I equal to 1 to I equal to r e to the power minus beta ei. Now this quantity, it is a very special name, it is called partition function, that we denote as p. Okay, p is called partition function, that is sum over e to the power minus beta ei, and this beta, it turns out that it is 1 by kBt, 1 where k is the Boltzmann constant, t is the temperature. Okay, so this is the so this is the partition function, and alpha and beta are now fixed. Okay, and this distribution that we see here, that is called Maxwell-Boltzmann distribution, and it looks like this curve. If energy is plotted on y-axis and number of particles in x-axis, it starts from when energy is 0, it will be n by p here. If energy is 0, then ni is n by p here, and it exponentially falls like this. So this comes when the particles are identical but distinguishable. The fact that it is distinguishable tells that the particles are classical. Okay, and the fact that electrons are not following electrons the free electrons are not showing the behavior as suspected has to do with this, that this distribution is not being followed. So let us look why the distribution is not being followed. So the crux of the problem is that we assumed the nature of particles to be identical and distinguishable. Okay, identical and distinguishable. But now we will see. So let us look what will happen. So what we see, if we increase the temperature, what will happen? If we increase the temperature, if we increase the temperature, then certain number of particles will increase at higher energy levels, and at low energy levels certain number of particles will come down. So it basically uh, so this is, if you try to plot this for two different temperatures, you will get this kind of distribution. Okay, and the fact that you are assuming the particles to be identical and indistinguishable makes them classical particle. Okay, but uh, at small scales, so if I give you two electrons, so let us look at what we mean by identical. By identical we mean that the properties or the attributes of the two objects given to you are exactly the same. For example, these two balls, one is red ball and one is green ball, these are non-identical. So this is blue ball and another, if had this been a blue ball again, then the sizes are different. So these are non-identical. But here you see, this is an yellowish ball, yellow ball, size are same, color is same. So these are identical. So as long as you have so in real world what it can be, if the mass is same, if the color is same, size is same, geometry is same, all the properties and attributes are same, then we call them identical particles. But is there a way to distinguish the two particles? So if I give you two different balls, can you distinguish them? So if I have two balls and if I like mix them in a box, do you have a method to distinguish that? Or if I send both the balls in a collision, is there a way you can find out, okay, no, this was the ball 1 and the other thing is ball 2? So that can always be done in principle, because the uh, because the Newton's law of classical mechanics are deterministic. So if I have particle, but let us say at what happens at small scale. At small scale, if I give you two electrons, if I give you two electron or say two proton, then you have the charge. Let's say two electron. The charge is same, the mass is same, the uh, charge is same, mass is same, and whatever the other attributes are there, all are exactly the same. Then what we say, that these particles are identical. Now the question comes, are they distinguishable or not? So at the forehand we don't know. What we do, we try to count, assuming that they are distinguishable or indistinguishable. And if and according to that, so if we assumed identical and distinguishable, we got certain distribution called Maxwell-Boltzmann distribution. Okay, had this been indistinguishable particles, then we would have got some other distribution. Now from other distribution, can we get the properties of the free electrons? If yes, then the electrons are indistinguishable. If no, then they are not distinguishable. So this is the approach. So what happens at so can we distinguish the two particles? So in classical mechanics there is certainty, and if we have the two balls, let's say the ball 1 and ball 2 at time t0, at time t0 we have this ball 1 and 2, we can use conservation of energy and momentum. They can collide, and we can determine the trajectory exactly, at which trajectory particle 2 can go, which trajectory particle uh, just a second, at which trajectory particle 2 is going and which trajectory particle 1 is going. That we can exactly determine in classical mechanics. But in quantum mechanics, we cannot, so there is no concept of trajectory. It later turns out that particle 1 and 2, when they are collided, we don't have a predefined trajectory. So, so that is why it is in principle not so you cannot actually distinguish between two electrons. So and how do we confirm that? So how, like earlier, so this is what we know because we know quantum mechanics by now. That is how we are saying that this is indistinguishable. What was the approach of the ones who were like initially researching on it? So they assumed that the electrons are indistinguishable. Corresponding to that, they found out the distribution. Now, does the results of experiments correspond to that distribution or not? So they did the experiment and it turned out that it is uh, the electrons are not distinguishable. So this is a very fundamental fact that differentiates classical and quantum particles. Classical particles are identical, but they are distinguishable. But in quantum mechanics, identical particles are the particles are identical as well as indistinguishable. You cannot differentiate. So particle 1 and particle 2, you cannot label them particle 1 and particle 2. Okay, so that's the crux of this discussion. So we can look into the some of the question answer of previous year based on this discussion. So let us start with the first question. I hope the discussion of theory part was clear. Or based on that, I hope this question should be solvable.
You know, kind of understandable, but overall it needs a lot. I think I have to do some kind of a practice. I think on the
Yeah,
derivation
but
part
I
to
think
understand.
based on today's discussion, you can solve these questions at least.
Okay.
So you can
Yeah.
try. What is the first
And
question?
we are not going to do derivations in the exams, right?
Derivations. I'm not so sure because I don't know.
So usually, how is the exam? It's like multiple
Yeah,
choice
that
type,
I,
or
I I have no idea of the exam
you don't have
rules.
idea?
Yeah,
Because you said previous year exam questions,
these
so I
are
thought,
previous year assignment questions. Like you'd be
oh, it's
giving
an
some.
assignment question.
Huh,
Okay, okay, not the exam questions.
not the exam questions. Yeah.
Okay, any chance that I can get a previous year question paper? I can have a look at it.
Yeah, that I also don't know because uh,
Would you be able to ask the professor and tell us?
yeah. See the way this NPTEL thing works is uh, like I'm a student in a different institute and they just
Yeah,
tell
you are
us
from
to,
ISC, right? And
yeah.
the
So
professor is from IIT
IT
Madras.
Madras. So and
Uh,
we don't communicate with the professor. We communicate with the NPTEL office. They just tell us, okay, this is the thing that you have to do. So that's all we do.
okay. Mhm. Okay, sir. Yeah, let's try these problems. Yeah,
Yeah.
I'll see how it goes.
Okay, so what about the first question? In a large particle system, only dash microstate is more probable. What do you think?
Three, three, right?
Why three? So what we saw, I'll just
We
go back
saw.
to theory once.
అవి రెండు
See,
మేలే డార్క్ ఆరెంజ్ ఈ
here
అవి
see,
ఎంత కలర్లే రెండు మేలే
here one
అది లైట్ గ్రీన్ ఎట్లా కనిపించింది
here one microstate is more probable than other. As the number of particles will increase, the most probable state, microstate, will become more probable than all other microstates. So it is that one microstate which becomes the most probable is the equilibrium state. So it is one microstate. I hope that is clear. Here, this is the most probable microstate. In three particle system, that's the
Which one? Which one is the most probable microstate, sir?
this is most probable, right? 60% of the times you will see the system to be in this microstate.
I don't see your micro this thing. That's why I'm not able to understand.
Huh?
I don't see your marker, say, your cursor,
You
when you're
can.
moving it.
Oh, okay, sorry. See here. Now you can see, right?
60%. The 6 ways. 1:1. Okay, so it's equilibrium
So
state. Got it.
this microstate is the most probable microstate for three particle system. For four particle system, the probability of this has increased 60%. Okay. If the number of particles will increase, then the most probable microstate, the probability of the most probable microstate will increase further. So that one microstate which has the highest probability will have uh, that is the one which becomes the most probable, and the probability of that is more than the sum of all others combined. In fact, it is so much more than all others are like they do not exist. Like, I hope that point is clear, because that is the crux of the that visualization is the crux of statistical mechanics. So the correct answer would be, it is, so the correct answer for this would be just anyone else would like to tell the first question answer? Large particle system, one only. Okay, so since it is said that only it is only one microstate is more probable. Okay, I hope this part is clear why it is only one.
So it is actually in a large multiplication, only one state means we are assuming that there is only one
See,
particle.
there are 10 to the power 28 around in 1 meter cube. Okay,
Yeah,
that
that's
10 to
about
the
span.
power 28 atoms, each of the atom will have certain energy state. Okay, and let's say Ni particles are in energy state Ei, and N2 are in N2 particles are in energy E2, and so on. Now there would be one particular, for if you fix the energy, then there would be one configuration of the system in which the probability of that microstate is so much more. When I say microstate, it corresponds to this mapping. So n not particle are in, sorry, n not particle are in energy E naught, so not, and one particle are in energy E1, and two particles are in energy E2. It is this mapping that we are talking about when we talk about a microstate. Is that clear?
Yes, now clear. Yeah.
Yeah. Okay, so what about the second question?
Identical and distinguishable particles, right?
Particles are identical
Identical and distinguishable.
and correct. Okay, what about the third
Both
question?
one, both one and two. Partition function is particle density and energy. Correct.
Just a second. Yeah. Yeah. What about the third question? Partition is a function. Partition function is a. So what
Both.
was partition function? If you remember, it is n divided by n is the total number of particles, and I equal to 1 to r e to the power minus beta ei. This was the expression.
Yeah. So we have the EI is the energy or um, epsilon I,
Yeah.
and Ni is your number of particles.
Ni is the number of particles. It is not particle density.
Okay.
Okay, so the correct answer is
Only energy. Yeah.
only energy. Yeah. Okay. What about the fourth question? Anyone else would like to answer? Revati or Anita? Okay, maybe you can only say.
So identical particles will quantum. Okay. Identical particles are indistinguishable in uh, classical mechanics, whereas it is distinguishable in
What in
quantum
classical?
mechanics.
Classical it is?
It is distinguishable and indistinguishable.
Yeah, correct.
Distinguishable, yeah.
Distinguishable and this is indistinguishable. Okay, what about the fifth? Oh, here. Okay, we just wrote it over here. Okay, what about this? This is known as what distribution? Or what statistics?
Basically, Maxwell Boltzmann, right?
Yeah, this is Maxwell Boltzmann statistics, correct. Okay, now you might remember this if you have seen the last week. Calculate the contribution, electronic contribution to the specificate. So, do you remember the formula?
Yes, yeah. CB is equal to. I just noted down somewhere. It is just look at it.
Yeah.
Uh, so did we calculate this last time? Because I thought it is 17.6 into 10 power 6.
I don't remember, but do you know? So, what would be the working formula here?
Uh, I don't remember it, so but at least I remember noting it in the notebook. I
Yeah,
don't
yeah.
have it.
You have it right now, or I can
No,
just.
I don't have it now.
Okay, so it is just 3 by 2 NFKB. Where this is the Boltzmann constant, Kb is equal to 1.38 into 10 to the power minus 23 in SI units. I think it is meter square kg second square Kelvin. Okay, and NF is the particle density. Okay, and you want to find for copper wire of unit volume. So so what would be the approach to find NF? Sorry, NF is the number density, not just density. Number density of electrons. NF is the number density of electrons. And copper, we have to assume that copper is univalent. So number of atoms is equal to number of electrons. Since it is univalent, number of electrons is equal to number of atoms. Okay, so how do you calculate NF? So you first find out what is the what is NF? Number of atoms per unit volume, right? Number of atoms per unit volume. From we can get from literature what is the density from gram per cm cube. You will get certain number, right? That
For
number,
copper. Yeah.
what you have to do, gram 1 centimeter is 100, 10 to the power minus 2 meter. So 10 to the power minus 2, 10 to the power minus 2 meter cube. So this is that number, gram into 10 to the power 6 per meter cube. Now that number into 10 to the power 6, since it is gram, now you put the atomic weight into Avogadro's number. That is the number of atoms per meter cube. So this is your NF, this value. Okay, so this calculation I have just done it here for you. So 1 meter, so the density is 8.96 gram per cc, and 1 meter cube will contain 8.9 and 63. So this is your atomic weight of copper.
Copper, yeah.
Yeah, if you just so this many atoms are there in 1 meter cube of copper. You just plug this in. So 3 by 2, this is the value of kb, and this is your nf. You plug everything in and you get 1.76 into 10 to the power 6. So the point here is to understand is that you have to use this formula, 3 by 2 nf kb. This is your working formula. If you know this all other things, you can just find out. Okay, let us now go to the second question.
The previous question, what was the answer, sir? The number.
Number question. Okay, so it was 1.76 into 10 to the power 6, and if you look here, 1.76 into 10 to the power 6. So 1.76 into 10 to the power 6 is 17.6 into 10 to the power 5. So this is your correct answer. Got it right?
Yes, sir. Yeah, got it.
Yeah. So basically, I mean, in the exam, this formula might come up, but yeah. So that's the thing.
Can you show that screen, sir? The calculation screen.
Oh,
Just
okay.
take a picture.
Yeah, sure.
Yes, sir. Done. Yeah.
Yeah. Okay. So what will be the mean squared velocity of the particles in free gas if the and particles mass and the electric charge are 2 times that of electron? Okay, so what it is saying, its mass m is twice me and the charge e is 2 times the charge of electron. Okay, then what would be the mean square velocity, and what is the working formula? This we got from the kinetic theory of gas. So half m v square, where v square is your uh, average square velocity. So this we get from kinetic theory of gas. This is just a formula you need to remember. Okay, from that v square is 3 by 2 kbt over m. Temperature we take by default as 300 Kelvin, room temperature, when nothing is specified. Kb is, mass, 2 times the mass of electron. You plug everything in and you get a value which is very close to 69 into 10 to the power 8 or 6.8 into 10 to the power 9, which is this part is clear, right? Is it clear?
Yes, sir. It is 69 to 8. Okay.
Yeah, cool. So yeah, calculate the drift mean free time of the particle mentioned in question 2. So what is the mean free time? So this is another formula we learnt in the last class. So this formula really important. Okay, the one. So what are the three formula we have already dealt with? CBE is
Yes.
equal to
Yes.
3 by 2 NFKB. This is, and half mb square is equal to 3 by 2 kbt, and another for this is another formula. Okay, and here what you want to find, tau. If the value of E is given, electric field is 1 volt per meter, right? Is 1 volt per meter, and mass is twice the mass of electron and charge is twice the mass of electronic charge. You have to find tau. The velocity v is given, v is 6 into 10 to the power minus 3. You put everything in and you get this 3.41 into 10 to the power minus 14 second. Okay, so this is your correct answer.
Yes.
Got it right?
Yes, sir. This is clear. Yeah.
And this is just put the formula, get the
Only
answer, type
rearranging
question.
the formula from drift velocity, you are taking the mean free time. Yeah.
Yeah. Okay, so So what about this? In metallurgical engineering, since the systems are typically molten metals, phase diagrams are usually composition versus temperature plot at what pressure. So if you look
Usually 1 atmosphere,
huh,
on a constant,
at
constant pressure, 1 atmosphere.
1 atmosphere, yeah, correct. What about this? Energy levels of a system are identifiable when the system is at. What about
Same,
this?
sir. Yeah, it's basically energy levels. Usually we call it CV or CP. CV is constant volume. CP is constant pressure, but it's actually
You
one
look at
one.
this. Energy levels of a system are identifiable. When we talk about energy levels, then the requirement is that volume has to be constant.
Okay, CV. Yeah.
Yeah. So it has to be at constant volume. Okay, here is another question which is based on that type of uh, counting that we did. So you can read the question. A system possessing total energy of 5E has 5 energy states. Okay, so system possessing total energy 5E means there is a system. In that system there are certain number of particles. Okay, so it is, and that certain number of particles is 7 particles. There are 7 particles in it. 1 2 3 4 5 6 7. So this is a system consisting of 7 particles. Volume is fixed, and what we want to do, and each of these atom, let's say this atom, each of these atom has these energy levels: 0 0 1 2 3 and 4. These are the energy levels of each of these atoms. Okay, so what is the most probable microstate if the total energy is 5E? So this system has, this is the system, it has 7 particles in it. 1 2 3 4 5 6 7. Total energy, volume is fixed, energy is 5E. So how do you find what is the most probable microstate? So here you have to find corresponding to this what are the microstates. How do you find that? So the trick is to, so here is the trick. This is how you should go about it. Just if you are not understanding the physics behind it, you can think of it as an algorithm. Okay, so what you should do, you look at what are the energy levels you have. You have energy levels 0 1 2 3 4. Now you decompose this 5E into these energy levels. So what you do is so you have this energy level 1E, and you have 7 particles. So what you are doing here, 1 2 3 4 5, you take first 1E 1E 1E, and whatever the rest is there, so you need to have 7 particles, right? So 7 particles, so other 2 particles are in 0E and other particles are in 0E. So that you need not write, but this is assumed. Okay, so after 1E you try to keep the first E constant and increase one of the energy level. The other level is 2E. So it is keeping 1 2E. In how many ways you can make? So 1E, E plus 2E. So to make it 5E, you need 2 more E plus E. And E plus 2E, another way you can write it as 2E. Okay, so if you just uh, then what you do, E plus 3E. So we did E plus E, E plus 2E, E plus 2E, E plus 3E, then E plus 4E, and then what we can do is, there is no E plus 5E that we like E plus 5E, it will exceed 5E. So you just keeping this constant, you can just try to increase and check in how many ways you can get these partitions. Okay, so we got this as partition 1, partition 2, partition 3, partition 4, partition 5, partition 6. Okay, these are each of the microstates. I hope this algorithm is clear.
Yes.
Yeah, or like you need to go through it once at your own time, or else this will be little. You need to think a bit here. Okay. So now let us look at this particular microstate. What this microstate means, each of the each of the particles are in this 1e energy level, and rest of the particles are in 0e. So that's what it corresponds to. 1 1 1 1 1 0 0. Total 1 2 3 4 5 6 7. San n equal to 7 and total energy is 5e. And the number of ways that can be done is 7 factorial divided by 2 factorial corresponding to this box, and corresponding to this box it is 5 factorial. And if you calculate it, it turns out to be 21. Okay. Similarly, you can do that for uh, let's say the second partition function. Okay, this for this e there are three 1e and 1 2e. So 1 2 3, these are the three 1e. One particle is in 2e and rest of the particles are in 0e. And if you look into the number of ways in which this microstate can be attained, it is 7 factorial by 3 factorial corresponding to this, 3 factorial corresponding to this, 1 factorial corresponding to this. So it is 140 number of ways in which you can do attain this configuration or this configuration. Okay. In how many ways you can attain this configuration? Now you draw this configuration here. One particle is in 1e and two particles are in 2e. See, 1 2e, other 2e. Got it right? One particle is in energy state, where is it? One particle is in energy state 1e and two particles are in energy state 2e 2e and rest in 0e. Similarly, you can calculate for others, and if you like you got right how this diagram can be made out of this.
Yeah, I'm getting it, sir. Yeah.
Yeah, and from this you can calculate the numbers, right? Once you have this diagram, I hope that is clear. Once you have this diagram, you can calculate that number, and it turns out that this microstate will have the largest number, which is 140. So the most probable microstate is this microstate, and it corresponds to 140. Understood?
So it will be 140, sir.
Yeah, it is 140. I hope the procedure is clear.
The 7 factorial divided by 1 5 fact 1 factorial 1 factorial 5 factorial. It's 42. Oh, 7 by 2 5 3 3 1. So here we are taking only two probability state, right? 5 has 5 energy state, 0 is 4 containing 7 particles, right? What is the number of ways in the most probable microstate? Okay, yeah, got it. Okay.
Got it right? What would be the most probable microstate in which the number of
Yes,
states
yeah,
is
it's
more?
clear. Yeah.
Okay. What about this? The Stirling approximation is valid for?
It's for all n, right? All n.
No, it cannot be all n, right? For example, if you take n equal to 1, no, n equal to 1, yeah, put n equal to 1, is it true? It cannot be all n, right? Put n equal to 1.
Is it small? It's n which is small?
No, why it should be small? So
Because
so do you remember where we used this
if
Stirling
you consider n
approximation?
which is large, uh, then we are considering
we
number
did
which are
we did this right, ln n, while we were about to calculate ln omega, do you remember omega was n factorial by product I equal to 1 to r n I factorial. Then we use logarithm of this. Then what we did, ln n factorial minus sum over I equal to 1 to r ln n I factorial. Then what we did after this, we put, see, this n is really large, that is why we said that we can use Stirling approximation now. This is where we had used Stirling approximation. So this is valid for large n, but nevertheless it, like, but try to put for n equal to 1, is it valid or not? N equal to 1, ln n factorial is ln 1, ln n factorial is ln 1, 1 factorial is 1, and log of 1 is 0. But n ln n minus n is 1 ln 1 minus 1, ln 1 is 0, so it is minus 1. So this equality doesn't hold at all. So Stirling approximation is not correct for 1. It is
so
not correct.
small n means it can be 1, 2, 3, anything, right? Not
1 2 3, see, it can be, so what it means is, how do I show, just a second, what it wants to say is, I'll just show you quickly. Oh, I don't have a, so if you calculate this, right hand side and the left hand side, uh, so it is valid for usually large n. So how large, you can just see it as, so for example, if I want to put, let's say, you are able to see the screen, right? Import, so what I'm trying to do is to show you when this is valid.
This is your Python code, sir.
Yeah, just I'm just writing a code to show you that part. Fact val is equal to, into I read fact. So what this will give you is, let's say, print factorial, let's say 3. So you can see the results here. 6, 3 factorial is 6, 4 factorial is 24. So what I'm going to do now, for in range 10. Yeah, so I factorial and so this is factorial I is your LHS, okay, and your right hand side is def. Right hand side is Stirling approximation. So what I am doing is, for an n it will return you n return n dot log n minus n. This is what it, so RHS n. Okay, so what it will give you now, you see. So for sorry, np dot log, or so what I'm going to do is LHS and RHS. You are able to understand the code, right? Or
Yes, I
what?
can understand the code. Yeah.
So what I'm doing is np dot logarithm of factorial n. So this is your left hand side of your Stirling approximation. LHS. Okay. You see here, for small values of n, this is your LHS and RHS. It doesn't work. You see here, the gap
Yeah.
is too much. This is your left hand side and this is your right hand side. This is 3, 1, 4, 3. Quite a big difference is there. But as soon as you have, like for large values, such as this gap becomes really small. Okay. So the point is, this Stirling approximation, it starts working when you have really large values of n. I mean, this you can just think, like take for granted as for now, but if you like do it carefully, you will see that uh, this and the type of numbers you have in statistical mechanics is 10 to the power 28. Okay, for that this equality really holds. I mean, for I mean, not exactly as equal, but the error bar is really less. Okay, so that's the point I want to convey. Okay, so let us go to the next question. So the correct answer here would be this large n.
Large N. Yeah.
Okay, it is the large n. What about this?
Partition function, right?
Yeah, this is partition function. Correct. And what about this? Like if you have studied the last week,
influence of ionic states on free electrons and influence of free electrons on each other, both.
Yeah, correct. What about this? This we just discussed few minutes before.
One.
Yeah, correct. Okay, so that's all for today. Thank you for joining.
Thanks a lot, sir. Yeah, this is
Yeah.
very useful.
Okay, we'll meet next week.